Good morning. In this lecture video, I'm going to explain a flip-flops. That means sequential circuit. So before I go to flip-flops, so digital circuits are broadly divided into a combinational circuit and sequential circuit. So combinational circuit in the sense output depends on only current input, and sequential circuit means combination again circuit as memory less. I mean it is not required to store the previous output. So examples are adders, decoders, and multiplex. So this is the block diagram of combinational circuit. Output depends on only input. But in sequential circuit, output depends on current inputs as well as previous outputs. So we need to store the previous outputs. Hence memory is required. Circuit requires a memory to store the past history of outputs. The best example is counters and flip-flops. So this is the block diagram. See, again it consists of combinational circuit, and the output is stored in the memory. Again that is available as a input to the combinational circuit. This is the final output of sequential circuit. This is the block diagram of sequential. So here memory is required, right? So memory is required. So we use flip-flops as a memory element, and flip-flop itself is a sequential circuit. So next I'm going to discuss flip-flops. So before that, we'll see the differences between combinational and sequential circuit. So in combinational circuit, output depends on only external inputs, and in sequential circuit depends on current inputs as well as previous outputs. So memory is not required here. So memory is not present. And here memory is present, and no feedback from output to input. But here there is a feedback from output to input. And in combination circuit, terminal behavior is represented by a truth table. In sequential circuit, they are represented by a timing diagram. So no time constraints on inputs and output, but there is a time constraint on inputs and outputs such as setup time, hold time, and minimum pulse width. So before go to actual flip-flops, we'll discuss bistable element. As the name tells, bistable means it is stable at two states. So it consists of cross-coupled NOT gates. Here two NOT gates, cross-coupled in the sense output of one NOT gate is connected as input to other gate. So output of upper gate is connected as input to the lower gate, and output of lower gate is connected as input to the upper gate. This is called cross-coupled NOT gates. Again, it is a simple sequential circuit because there is a feedback from output to input. Its states are not controlled. I mean, we cannot change the state. So only one state variable, but two possible states. They are either set state or a reset state, and it is central to the flip-flop circuits. I mean, flip-flop circuits are constructed from the concept of bistable element, and the circuit has two outputs. They are Q and Q bar outputs. The structure involves a feedback. Now analyze the state. Stable at zero state. That means Q is equal to 0, Q bar is equal to 1. So Q bar output. This Q bar output is connected as input to the upper gate. Again it is 1, and its output is 0. So it is always 0. Again this 0 is connected as input to the lower NOT gate. So again its output is 1. So it is always stable at 0 state. And stable at 1 state means Q is equal to 1, Q bar is equal to 0. Again this Q bar is connected as input to the upper gate. Its output is 1. Again this one is connected as input to the lower NOT gate. Its output is 0. So it is always stable at a 1 state. So we cannot we cannot change the state of the bistable element. It is decided at the time of manufacturing. So now we'll see flip-flops. Again, flip-flops are a memory element. They are used to store the binary information. That means either we can store 0 or 1. So it is a 1-bit storage element. So circuit made up of assembly logic gates. That means again flip-flops are made up of logic gates. Even though logic gates have no storage capability, by using several gates connected together, we can ensure the storage information. There are three classes of flip-flops. They are latches, master slave flip-flops, and edge triggered flip-flops. So we'll discuss one by one later. Let's see SR flip-flop using NOR gate. That means this is the circuit diagram. So it consists of cross-coupled NOR gate. That means upper NOR gate. We can say upper NOR gate or NOR gate 1 or NOR gate 2. Output of upper NOR gate is connected as input to the lower NOR gate, and output of lower NOR gate is connected as input to the upper NOR gate. So it consists of cross coupled NOR gate. It is also called as SR latch because it's a one class of flip flop. So it has two inputs, S and R. S refers set input and R refers reset input. So there's two outputs, Q1, Q bar. Q is normal output, Q bar is complementary output. So state of the flip flop is decided by the Q output. That means if Q is equal to 1, the state is set state. If Q is equal to 0 and Q bar is equal to 1, the set is reset state. So here timing of the output is not controlled. That means the output responses the changes in input immediately. Hence, inputs are called as asynchronous. They are not synchronized with any control input. So here Q1 denotes present state. That means state of the device at the time of signals are applied. And Q1 plus 1 denotes next state. That means response of the device at Q1 Q bar terminal as a consequences of applying the various inputs. So let's see the operation. We designated upper NOR gate as NOR gate 1 and NOR gate 2. And remember here R is corresponding to Q and S is corresponding to Q bar. So before go to the operation, we'll see NOR gate. See, if one input to the NOR gate is fixed, whatever may be other input, output of NOR gate is 0. Because suppose if other input is 0, so 0 plus 1 is 1 and its complement is 0. So output is 0. If other input is 1 also, output is 0. That means it can be either 0 or 1. Other input can be 0 or 1, output is 0. So with this concept, let's verify the operation. So first we'll consider the different cases. Case 1, when S is equal to 0, R is equal to 0. That means observe the diagram. R is equal to 0, S is equal to 0. As we analyze it, if one input of NOR gate is fixed to 1, whatever may be other input, output is 0. But if one input is 0, output depends on other input. That means output of NOR gate 1 depends on other input, that is Q bar. Similarly, output of NOR gate 2 depends on other input, that is Q. So we must know what is Q and Q bar presently. So that is called present state. So let it be, let the flip flop is in 0 state. 0 state means Q is equal to 0, Q bar is equal to 1. And this Q bar is equal to 1 is applied as input to the upper NOR gate. So again its output is 0, and that 0 is applied as input to the lower NOR gate, I mean NOR gate 2. So its output becomes 1. Okay. So flip flop remains in 0 state. That means we assumed Q is equal to 0, Q bar is equal to 1. We got again Q is equal to 0, Q bar is equal to 1. That means same remains in the same state, that's 0 state. So we'll write the corresponding truth table. It consists of inputs S, R and present state Q1, Q1 bar, and next state Q1 plus 1, Q1 plus 1 bar, and we'll write the state also. So here S is equal to 0, R is equal to 0. Present state we assume 0, 1. I mean Q is equal to Q1 is equal to 0 and its complementary output 1. So you got the same thing. Okay. Now we'll assume flip flop is in one state. That means Q is equal to 1, Q bar is equal to 0. So this Q is equal to 1 is connected as input to the NOR gate 2. So first we'll verify the output of NOR gate 2, that is 0. Okay, and this 0 is connected as input to NOR gate 1. Then output of NOR gate 1 is 1. So flip flop is in one state only. Q is equal to 1, Q bar is equal to 0 means one state. Again we assumed one state, we got same one state, so we'll write it in a truth table. Okay, one state we assume we got one state. So thus if both the inputs are 0 0, then the output state does not change. So same as present state, same as present state. Now we'll see case 2. When S is equal to 0, R is equal to 1. Okay, so means R is equal to 1. Okay, so let's assume the flip flop is in 0 state. That means Q is equal to 0, Q bar is equal to 1. So even though R is equal to 1, no, analysis starts from on OR gate 1, because whatever may be other input, its output is 0. output of NOR 1 is 0, and this 0 is connected as into the NOR 2, so and its output is 1. Okay, that means we assumed 0 state, you got the same 0 state, q is equal to 0, q bar is equal to 1. So flip-flop remains in 0 state. Okay. So if s is equal to 0, r is equal to 1, if the present state is 0, 1, next state is also 0, 1. And assume flip-flop is in one state, that means q is equal to 1, q bar is equal to 0. Again analysis starts from NOR gate 1. So output of NOR 1 is 0. Okay, that means q becomes changes to 0, and this 0 is applied as input to the NOR 2, and its output becomes 1. So q bar changes to 1. That means flip-flop changes to 0 state. 0 state. That means this is the one. If it is 0, 1, I mean s is equal to 0, r is equal to 1, present state is 1, 0, next state is 0. So from this we can say if s is equal to 0, r is equal to 1, flip-flop remains in 0 state or enters into 0 state. In this case remains in 0 state, and this case enters into 0 state. So 0 state means it is reset state. Okay. So whenever r is equal to 1, it enters into reset state. Similarly, so we'll assume we'll take consider third case when s is equal to 1, r is equal to 0. Okay, s is equal to 1, r is equal to 0. Again assume flip-flop is in 0 state. So here analysis starts from NOR gate 2, because one input is 1, whatever may be other input, its output is 0. So NOR gate 2 output changes to 0, q bar becomes 0. That q bar is applied as input, so q becomes 1. So that means flip-flop changes to one state. So we assumed 0 state, q is equal to 0, q bar is equal to 1. We got q is equal to 1, q bar is equal to 0. That means changes to one state. Okay. Present state is 0, 1, next state is 1, 0. And if you assume one state, that is q is equal to 1, q bar is equal to 0, again analysis starts from s is equal to 1. So its output of NOR gate 2 is 0, and this 0 is applied as input here, its output is 1. That means remains in the one state, remains in the one state. So from these two rows we can say if s is equal to 1, r is equal to 0, flip-flop remains in one state or enters into one state. That state is called as set state. Clear now? So that means if s is equal to 1, enters into set state. So we consider fourth case when s is equal to 1, r is equal to 1. So both are 1, 1. So when both are 1, 1, both the output of NOR gate is forces to 0. So output of NOR 1 is 0, as well as output of NOR 2 is also 0. Okay. So they are not complementary. Outputs are not complementary. Hence, this state is not allowed. This state is not allowed. Okay. So that state is called as forbidden state. That state is called as forbidden state. Okay. Fine. So from this truth table, so we can write a reduced truth table consists of function table consists of only s, r, and the next state q1 plus 1 and q1 plus 1 bar. So from these two rows we can say whenever s is equal to 0, r is equal to 0, same as present state q1 bar. And from these two rows we can say it is enters into reset state, that is 0, 1. And next case, from these two rows we can say it is enters into set state. So q1 is equal to 1, q1 bar is equal to 0. And from the next two rows we can say forbidden state. So this is the function table. So from the function table I can observe when both are 0, 0, same as present state. When r is equal to 1, enters into reset state. When s is equal to 1, enters into set state. When both are 1, 1, 0, 0, so forbidden state. Clear now? So this is about yes, I'll continue in the next video. Thank you.